The days where students will be ready to wait for years to understand the full cycle of a subject that they are studying are gone. In my days, the professors used to be so stingy when it came to unleashing the truth. They would answer the questions, but in bits and tits, slowly, carefully. Either they thought that the students were so foolish that they could not understand the full cycle in one lecture, or they were guarding their position of authority for as long as they could. Everybody wants to understand the full cycle of whatever they are studying or experiencing. The main reason is that it offers them the big picture. Also, it gives them certain degrees of freedom to navigate the subject and make choices. Why do we think people, especially young ones, love romance movies? Well, it's because it shows them the full cycle of love. It starts with two people who don't know each other, then they fall in love, the relationship grows, then something happens, then the relationship breaks, and there is a learning, and then it mends back, then there is happily ever after. That's a full cycle I'm talking about. It's possible in an hour, so why not with subjects like statistics? By knowing the full cycle of romance, the student can navigate his own romantic life and make the necessary choices at every steps, being guided by the full cycle that he saw in movies. It is disputable, of course, whether the full cycle of love was portrayed correctly or incorrectly in the movies that he saw, but since the vacuum was there, the movies filled them, and young lovers use them as references. So now I want to take you into this movie of the full cycle of statistics, what it is all about. To define statistics, I will use the physical sciences as a comparison. This exposition is based on the diagram below, so you can refer to it as I go along. Physics is one of the physical sciences, and it is the study of non-living physical objects. Chemistry is another physical science which studies non-living molecules and elements and how they interact with one another. Biology studies living organisms. In the same line, what subject studies non-physical, non-living, non-real, or abstract events and phenomenon and the relationship between them? Aha, you got it. That's statistics. Below you can see the diagram of a metal wooden cube. Physics is in the business of measuring its property. Chemistry would measure the elements that it's made of, and biology might be concerned about the wood it comes from. But for this particular section, we'll stick to the physics of the cube. In physics, the goal is to obtain a fixed deterministic value of the cube using tools like a ruler, a caliper, or a weighing machine. The question that we want an answer to is what is the exact length of the cube's side? The result we would get from this simple, basic physics experiment, for example, is that it's 10 centimeters. That would be a known fixed value with only trivial measurement error. So we can be certain that it's 100% 10 centimeters because the ruler or the caliper says so, so it's a fixed law. Now let's flip the coin and understand what this abstract science called statistics measures. Like for the example of the physical science, I used the cube, where there are thousands of other that I could have chosen, like light, gravity, salt, rare metals, plants, the digest system. For statistics, I chose the link between smoking and cancer to illustrate the full cycle, knowing that there are thousands of other phenomena that could have been used. So Newton studied gravity and explained it using physics. But how to explain the event of a cancer and its possible link with smoking? This is the realm of statistics. So the goal here is to obtain a probabilistic value static certainty of smoking causing cancer. The tools used is inferential statistics, and in it are measures called ANOVA, z-test, and p-value, among others. The question we want to find an answer to is what is the likelihood that the link that we have suspected between smoking and cancer is not due to random chance. The results we should get is what we call the p-value based on real data that have been repeated over and over in this particular case of smoking and cancer. The p-value is equal to 0.0001. It means that the risk of being wrong, that is the link between smoking and cancer, is not due to random chance, is very low here. Alternatively, by converting that into percentage, this means that there is 99.99% likelihood that there is a relationship between smoking and cancer. And that's the full cycle of statistics. To us, it might seem so obvious, but it was not so before this study was conducted. People, even the medical professionals, actually mocked this hypothesis that smoking caused cancer. So what statistics did was to measure the abstract phenomena and events that smoking and cancer relationship was. Through its established definitions, rules, and procedures, we could explain causality, randomness, and uncertainty of various events. Just like we could measure phenomena in the physical sciences for entities that were physically present and observable with our physical senses. Now let me take you through the 10 steps that are part of this full cycle of statistics. In the earlier paragraphs, I made it sound so simple and fast. It was like the trailer of the movie or a quick summary. You understood the plot line. That's good. The real full movie or full cycle of statistics can be much longer, but I will expound on the 10 steps into a short movie instead of 10 seasons serial. So start with step 0 or observation. As you can see in the diagram, there is a scatter diagram. There are 3 examples. The x-axis are the values for one of the variables, like smoking in our case. Then the y-axis is the values for the other variable, which would be the dependent one, or in our case, cancer. The relationship between the 2 independent variables and dependent variables could be one of the 3. Each data point could be seen increasing as if following a straight line moving upwards to the right. This would mean that there seems to be a positive correlation or proportional relationship. The next possibility is the second diagram, where the data points arrange themselves in such a way that a straight line moves down to the right as the value of x increases. This would show an inverse proportionate relationship. It would mean that the more a person smokes, the less there's a chance of cancer. And in the third diagram, you can see that the data points are scattered all over, showing that there doesn't seem to be any kind of relationship between the two variables. So this is descriptive statistics. We are just seeing the data points. So in our movie of the link between smoking and cancer, most likely the first scientists must have seen a relationship reflected by the first scatter diagram. So this is enough to propel them to step 2, which is the research question and hypothesis. As we have already established, there are 3 main branches of statistics. For descriptive statistics, we need a research question, but we don't need to make a hypothesis statement. For inferential statistics and predictive statistics, we need both the research question and the hypothesis statement. Now, in the case of this smoking and cancer, first did a descriptive statistics and asked how are smoking and cancer related, and the scatter diagram gave us the answer. Now that's not enough for the world to believe it. We need inferential statistics to prove it. So we need a hypothesis. We need to make a bold claim that can be falsified, which would then be a null hypothesis. So here our hypothesis will be smoking causes cancer. And the null hypothesis will be the link between smoking and cancer is random, and so there is no causation between the two. Predictive statistics would have to answer a question like how much smoking increases the probability of getting a cancer. Then we move to step 2, which consists of the review of existing research. It's quite straightforward. The objective is to not waste time if somebody else has already done that particular research. Also, we can use the findings to help in the step number 3, which is the study design. What the researcher does in this step is to find the answer to 4 main questions. What data will you collect? How will you collect the data? How much data is enough? And what other variables might interfere besides the one you are trying to study? Although I'm highly simplifying the statistical study of the link between smoking and cancer, I will require you to take it with a pinch of salt, because I'm just trying to show you the full cycle in short exposition. So to answer the first question, I'll need to collect data on how many cigarettes a group of people smoke. Then I'll need to ask people in the hospital suffering from cancer if they had been smoking before, and if so, how many cigarettes they had smoked, over how long. This takes us to the second question. I would be sending my staff to the various hospitals and make them interview the cancer patients. Logical question is the third one, although there is a standard for the number of data required. Here, let's say that I'll ask them to get the interviews of 500 cancer patients. And the last question is pertinent. I should make sure that they should focus on lung cancer patients more than other forms of cancer patients. So now I've got the study design. Next step is the preparation of the questionnaire. Again, this has to be methodically prepared to avoid various kinds of errors that are quite standard in statistics, but that I will not go through here to keep with the brevity of the full cycle movie that we are watching here. Then we flow to the next step 5, which is about collecting the data. Finally, we move to the step 6, where we enter the data into a software, if not just an Excel sheet. Then we move to step number 7, where we do descriptive statistics or data exploration. Calculate the mean, median, mode, standard deviation, range, frequency, quartile, trend. The earlier scatter diagram was part of the step. The next 3 steps I have combined as a single unit for this full cycle of statistics movie. It consists of step 8, hypothesis testing, step 9, report writing, and step 10, interpretation of results. This is the inferential statistics part and the predictive statistics part also. As you can see in the table, the final object output that we want from the study is to find the p-value that we have already discussed earlier, then the z-score, the regression coefficient, then the predictive model or probability score of the relationship between the phenomena that we are investigating. In order to do that, you have to use some other tests based on the type of data that is being analyzed. The data could be categorical, like yes or no, or they could be numerical, like rating between 1 to 10. So this gives us 3 possible combinations, and as shown in the table, each combination is served by different types of statistical tests. Then they are combined to give the final output that we just discussed. Voila, you've completed the 10 steps of statistics. But let's look at the results and the interpretation in the column table next to 10 steps box. So this is the actual result for the study of the link between smoking and cancer. The first column shows the statistical output. The second shows the unit or range of metric for a positive value. The third one shows the actual value in that particular study. Then the fourth column shows the interpretation of that number in the context of the relationship we are studying, that is of smoking and cancer. So let's start with the chi-square. Normally its range is from 0 to infinity, but in this study it's found to be 1450, which is a high value. Now what this means is that the observed rate of cancer incidence among smokers is significantly different than the rate among non-smokers. This indicates a strong association between the two categories. This implies that even though I did not mention it in the step 3 in my full cycle exposition, this was not only a longitudinal study of smoking and cancer, but it was the experimental study where there was a control group and an experimental group. So the data was collected for cancer patients who did not smoke and cancer patients who smoked. And this is the test result that we got. Then the correlation coefficient, or Pearson's R, shows a value of plus 0.68, where the range is from -1 to +1. The interpretation is that there is a strong and positive correlation between the number of cigarettes smoked daily or cumulative exposure and the likelihood of developing lung cancer. As one increases, the other increases. As you can see in the best statistical test table, the chi-square test was done for the categorical versus categorical data of the study, and the Pearson or correlation coefficient R test was done for the numerical variable or numerical versus numerical part of the study. And both of them have shown that there is a significant and positive relationship between smoking and cancer. Now this takes us to the p-value. The range is from 0 to 1. If the p-value was 1, that means that it would be a random occurrence, like throwing of a dice or the flip of a coin, and a value of 0 for p-value would be like Newton's apple falling to the ground. There is no doubt about that. Once the apple leaves our hand, it will fall on the ground. So in the case of this smoking to cancer link, as we discussed earlier, the p-value has consistently be found to be less than 0.1%. So the interpretation is that the probability of observing a relationship this strong by chance alone is negligible. The link is highly statistically significant, and we reject the null hypothesis that there is no relationship. Remember, it was the one we established earlier on, step 1. Then let's look at the other two statistical output, which are not exactly predictive statistics, but leaning towards it. It's called the regression coefficient. The unit is Rix per cigarette per day. It could be any value of beta. Here, beta is given as 0.025. So it means that for every 1 unit increase in the average number of cigarettes smoked per day, the predicted relative risk of cancer increases by 0.025 or 2.5% for relative risk. It gives us a measure. This is what we hear on television usually, that every cigarette we smoke reduces our age by a certain number of days or years. The final statistical output is the predicted value of y. It ranges from 0 to 1. Here the value is 0.75. The interpretation is that the model predicts that an individual with a specific high-risk smoking history has 75% probability of developing lung cancer during their lifetime. And that comes from the predictive model. That's it. So now you've seen the full cycle movie of statistics from step 0 to step 10. That's what statistics is all about. It's not that hard, is it? You don't have to feel threatened by it. Most importantly, in this section, I didn't want you to have to wait for decades like I had to wait in order to understand this much. And I hope that this will help you love statistics like it should be loved, because it's such an important subject.